This lecture is about Kepler's third law, also known as the law of periods. This will be the one that we are most responsible for because it gives us some intuition about the period of rotation of celestial bodies. The satellite, we're going to start with the derivation here. So satellite of mass m sub p orbits a star of mass m sub s at an orbital distance of big R. And we're going to derive a relationship between the period and the orbital distance. So essentially, we need to eliminate the speed. And we've done this before with the first half of our circular motion. So I'm going to invite you to start with Newton's second law and actually go through the derivation to get the expression for satellite speed. So pause the video, go ahead and try it, and then we'll double check our work. All right, you're back. Hopefully you did that. You should have ended up with the satellite speed being equal to square root of big G, mass of the star or the central object divided by R, not squared. That is our expression for the satellite speed. So now we are going to eliminate V and solve for T. So we're going to use our expression for linear speed for things that move in circular motion and state that the velocity is going to be equal to 2 pi r over t, and we're going to derive an expression for the period in terms of radius and known constant. And we're going to get rid of the square roots. That's important too. So flipping back over. So I'm going to kind of start with the fact that v squared, oops, I'm on the wrong marker. V squared is going to be equal to g mass of the sun over r. So basically I'm squaring my final answer or using the step right before that. So v squared is going to be 4 pi squared r squared over t squared, and that's going to be equal to g mass of the sun divided by r. So these r's do not cancel because you have one in the numerator and one in the denominator. So I'm going to cross multiply, and I'm going to get 4 pi squared r cubed is going to be equal to t squared g m sub s. And now I'm going to solve for t, and I get t squared is going to be equal to 4 pi squared over g mass of the sun times, r cubed. Yeah, got that right. All right, so what does this kind of show us? This is kind of what's the consequence of this relationship? So if we look at everything that's in this bracket right here, these are all constants. And if we look at m sub s, so let's have m sub s as the central object. If I want to figure out the period, all I have to look at are the different orbital radii of all different planets orbiting around the same central object. They will have that ratio of t squared to r cubed is going to be equal to this constant value, the 4 pi squared g mass of the thing in the middle. So as long as all of these things are orbiting around the same thing in the middle, it's kind of interesting that you have just this whole bunch of constants. And Johannes Kepler, along with Tycho Brahe, collected an enormous amount of data, timing and looking at orbital distances and periods of all the celestial bodies in our solar system. And they came up with this relationship of t squared over r cubed was equal to some constant value. It was the same. They had no idea what it meant because it took Isaac Newton to come along with his universal gravitation to give some meaning behind it. But it was pretty amazing that they collected all this data and found that that relationship t squared over r cubed was a constant value. So what does that mean for us? It means, well, if I graphed t squared versus r cubed, I'm going to get a linear relationship where the slope of that line, you guessed it, is equal to 4 pi squared g mass of the sun. And again, this ms is the central object. It's whatever everything else is orbiting around. So you could have all kinds of data on orbital periods and orbital distance as long as they're orbiting around the same thing. So what kinds of combinations could you have? You could have the sun with all the 8 or 9 planets, depending on whether you count Pluto or not. You could do artificial satellites around the planet Earth. You could look at the moons of Jupiter or the moons going around any other planets. So there's a lot of planets in our solar system that have multiple moons. As long as you're looking at the same central object, that ratio for t squared to r cubed is going to be constant. Again, using ratios with this idea, the t squared over r cubed, let's say for Earth, would be equal to the ratio of t squared versus r cubed for Mars. So this was the orbital period of Mars. Orbital period of Mars squared divided by the orbital distance of Mars cubed. That ratio would be constant. And kind of the neat thing about this is that units don't matter. So as long as they're the same, you do not have to have period in seconds and r in meters. They can be anything. And in fact, when we start talking about astronomical data, there are some units that are more commonly used. T can be in years, and sometimes it's relative to Earth. So we might say that Neptune's orbit is seven Earth years or something like that. I don't know what the number is exactly, but you could put it in numbers relative to Earth. And then in the R, there can be something called astronomical units. So AUs is an astronomical unit. And basically, that astronomical unit is in multiples of the Earth-Sun distance. So 1 AU is equal to the orbital distance of the Earth to the Sun. So again, you can have like 3, 4, 10 AU is much more easily dealt with than having to deal with, tens of thousands of kilometers of distance and plugging all that in our calculator. So let's look at a very simple application. If you have two moons orbit the same planet, again, that is very key. So I have one planet that's in the middle here, and we have two moons. So this would be like moon 1 and moon 2. And this one has like an orbit that looks like that. And let's say that this one has a different color orbit. This one's got an orbit that looks like that. So both of those moons are orbiting around the same planet. Hopefully that makes sense. What is the orbital distance of moon 2? So we can do the period squared of moon 1 and the orbital distance of moon 1 cubed and set up a ratio with moon 2. So moon 1 has an orbital distance of 0.5 AUs cubed and a period of 165 Earth years squared, and that has to be equal to moon 2 has a period of 300 Earth years squared, and then the orbital distance of moon 2 cubed. So we can set up a simple ratio here and solve for R2. So again, I'd kind of check and make sure that you can use your calculator and find the cubes and cube roots of that. So try that number, and I'll turn off the video and just plug it into the calculator. All right, hopefully you have plugged that into your calculator, and you would get R2 is equal to 0.74 AU. Again, don't forget units on all of these things. All right, and that finishes up Kepler's third law.